it's an honor for me to be here to present Dr. Elias Franses for the Celebration of Faculty Careers Colloquium. Now, the Celebration of Faculty Careers Colloquium was a direct outcome of the strategic plan, the college strategic plan a few years ago, and two specific things, outcomes from that plan, were the idea of Faculty of 2020, the idea of professional development at all stages, but also there was a second outcome there which related to the idea of better aligning our promotion, tenure processes with the evolving goals of the college and its leadership mission. And so at the time, a desire was expressed to have a review post-tenure of the accomplishments of faculty and their plans for the future, which would be then followed by a meeting with the dean and heads to lay out the view moving forward from there. So that's how the process started, and Professor Elias Franses is going to be our speaker today. Dr. Franses got his diploma in chemical engineering from the National Technical University in Athens, later the PhD from the University of Minnesota, and he's been at Purdue since 1979, except for a brief stint in Washington, D.C.
Yes.
As a program director for the National Science Foundation. Many of you probably know about his research. We'll learn a lot more about it. I've certainly followed his research and DLVO interactions for a while, so look forward to this talk. So without further ado, Dr. Franses.
Thank you. I'm very pleased and excited to give this talk today. Before I continue, I'm going to make sure everybody can listen to me in the back and also in the recording, because I have been wired twice. Thank you. I have been preparing for this talk for the last 36 years. And this talk gave me the opportunity to review what I did really for the last 36 years. So it's a great opportunity to reflect. And then, so I will describe to you first, briefly, without going into too much depth, some results from the first 3 stages of my career here at Purdue. And then I will go in more depth and more detail in the most recent area, which is reflected in this title. So my career has been working with a lot of things, but it has been primarily centered on the science and applications of surfactants, interfacial phenomena, and colloidal phenomena. I'd like to give you some background, just to make sure you can follow what I'm going to talk about later. A surfactant is usually an amphiphilic molecule, which means it has a polar group and a non-polar chain. Oops. Postpone. That has the main properties, thank you, Ramki, the main properties of adsorption at interfaces. Adsorption, we mean a preferential concentration on the surface compared to the bulk. Okay? So adsorption can occur at air-water interfaces, and then it is important in foams and in lung surfactants, which I will explain. It's also important in oil-water interfaces, important for emulsions and enhanced oil recovery. And finally, it's important in solid particle water interfaces for inks, paints, and so-called nanotechnology. In addition, non-soluble surfactants are also important, and they form what is called insoluble monolayers, or Langmuir monolayers. And insoluble surfactants are also called lipids if they have a biological origin or a biological relevance. And then there are applications in so-called Langmuir blodgett films that are produced by pulling a solid surface from a lung with monolayer, and also lung surfactants and lipids. The most important other property of surfactants is spontaneous aggregation in solution, forming so-called micelles. If you have a surfactant like this in water, okay, it can form, as I said earlier, monolayers at different interfaces. It can form micelles, which are compact aggregates that have a hydrocarbon interior. In addition, some surfactants which have double chain can also form bilayers, bimolecular layers, either flat, or if they become round, they form vesicles, liposomes. These are classified in two categories: unilamellar vesicles and multilamellar vesicles. Okay? So, surfactants absorb and they form aggregates. Okay? Why? Let me remind you the reason why. It's called the hydrophobic effect. Okay? Hydrophobic effect means water fearing, not water hating. Okay? I don't want to go that far. But why do molecules aggregate? The first idea in the early 20th century was because of enthalpic, because of energetic interactions. But it was discovered later, remember now, that dissolution increases the entropy, therefore aggregation decreases the entropy. So aggregation should not be favored entropically. However, the key here is the structure of water. The structure of water is such that it forms hydrogen bonds, and then close to the hydrocarbon chains, water molecules order. They decrease their entropy. Therefore, when you have aggregation, when the hydrocarbon chains are separated from contact with the water, either in a small aggregate called pre-micelle here or in a big micelle, the entropy of the water molecules increases upon aggregation. Therefore, the total entropy of aggregation is positive. So aggregation and adsorption, in these cases, is entropy-driven. And the enthalpy can be positive or negative. It doesn't really matter very much. So surfactants form micelles, adsorbed layers, and vesicles. And here I will have a very simple-minded view of all this, in addition to things more in depth. Are the micelles good or bad? Okay? The same for the vesicles. Are they good? Are they bad? I don't know. Let's find out about it. What are the practical implications of all this? So, here starts my career. I came to this country in 1974. I went to the University of Minnesota, where I worked with Professors Scriven, Davis, and Miller. I had 3 advisors. And then 2 collaborators, Puig and Talmon. Okay? So the first stage of my career is my PhD thesis, and then subsequent research. It was both fundamental and practical. But the main motivation was enhanced oil recovery. Those of you who are a little bit older than Brian, sorry, Brian. Brian was not born when I was doing this research. That's why I have fatherly feelings. Did not know about the energy crisis. Yes, it's different levels. At that time, the price of oil was $40 a barrel, $50 a barrel. And I have to tell you a story about that. Actually, I have a lot of stories today. I had to curtail them a little bit because my talk is recorded. At that time, everybody thought, including myself, that in 25 years there will be no oil. Okay? By the way, this prediction has been always correct. It's correct today. And 25 years from now, it will also be correct. So we thought oil is the thing. Let's do it. Let's do a lot of research, recover recover as much oil as possible. Oil is produced from underground reservoirs, and only about 20–30% is recovered. The rest remains stuck in the porous media. And the main reason for that is the presence of oil-water interfacial tension. So it's an interfacial phenomenon. And if the interfacial tension is normal, in the normal range between 30 and 10 millinewtons per meter or dynes per centimeter, the oil it's very difficult to mobilize the oil. To do that, you have to produce unprecedented low interfacial tensions, called ultra-low interfacial tensions. And at that time, the action was in using water, surfactant, and alcohol microemulsions, for which I will not going to talk about very much. At that time, I started studying liquid crystalline particles. And liquid crystalline particles were shown to have the capability under certain conditions to produce very low interfacial tensions. And then we said, well, let's try to produce vesicles. It was interesting, fundamentally, but we found out in that particular case, the same surfactant dispersion that had vesicles was much worse in producing ultra-low interfacial tensions than liquid crystalline particles. Therefore, to keep my theme, vesicles were bad. At that time, of course, my PhD thesis finished, so I escaped. And we didn't follow this very much. But it's interesting to consider, when you do research in this area, to consider various options, okay? And then in 1984, the bottom fell out of the oil prices. And so my research, some of the research I started here on liquid crystals and vesicles was no longer very grant-wise relevant. And therefore, I had to do something else. So, before I figure out the specific application area of what to work on, I was interested in more fundamental research, sort of like fishing expeditions, as they call them. So I started talking about thermodynamics of mixed micellization, okay? It's a theme. Conductivity of micelles, with one very bright undergraduate student from Purdue. I was able to publish a paper that is really very highly rated. Everybody who does work on conductivity of micelles cites this paper. Otherwise, they are in trouble. Langmuir monolayers, rheology of dispersions. Is Jim here? He is responsible for some of that. Okay? Started collaborating with people. And then the students were this, and then the collaborators were this. I published several papers. I learned more about micellization, adsorption, etc. And at that time, I studied some surfactants called SDS, sodium dodecyl sulfate. Remember that, SDS. And I also, in the conductivity of micelles for SDS, we understood this well. We also studied conductivity of vesicles, vesicular dispersions, one of which was called DDAB. Mark this in your brain, please. SDS, DDAB. So, this area finished more or less, and then sometimes in the middle 1980s, I used to have an office next to Dr. Hahnemann, pediatrician of our son Joseph, biomedical engineer, and then actually, doctors talk in a very blunt way. He told me around 1984 or 85, after he spoke to Nick Peppas about me, he asked me the following questions. I still remember more or less. Quote, Elias, I heard you know something about surfactants. Uh-oh, I said. It's time for insults. What do you know about lung surfactants, pulmonary surfactants? I said, nothing really. But he said it's an interesting problem, okay? It is a mixture of lipids called lung surfactants, sometimes proteins, stabilize lungs against collapse. it's a major problem of premature infants. I said, oh, okay. And then it's related to the surface tension of an aqueous layer at the lung-air interface. It's a surface tension phenomenon. It's a surfactant phenomenon. Oh. There are so-called lamellar bodies which are insoluble surfactants in the liquid crystallites. And most importantly, what intrigued me was, here we have a dynamic, time-dependent surface tension. And the doctors at that time, who in my opinion knew nothing about interfacial phenomena, that's not true. They say you need this pressure difference to inflate the lungs. If the pressure difference is too high, because the surface tension is too high, the lungs will have a problem. It's a surface tension problem. I said, okay. In addition, the surfactants, which decrease the surface tension from 7 to 30 or at most 20, can produce, under dynamic conditions, pulsating area as you breathe at 20 RPM, extremely low dynamic surface tensions, as low as 1 dyne per centimeter. 1 dyne per centimeter? I don't believe that. Cannot be more than the equilibrium. So I started working on this problem to understand the so-called super low dynamic surface tensions, which are related to the surfactants and the lipids. And then I made this transition. I worked for 25 years in this project with many students, as I will tell you. And then in 1996, I went to Skip Fest, the 65th birthday party for Professor Scriven. And they asked me to give a talk. I said, okay, I'll give a talk. And he said, just tell us your career before and after, you know, what happened. And how can I explain to these people now? Enhanced oil recovery, ultra-low interfacial tensions, lung surfactants, super low. So I tried to make it easy for them to understand. Hopefully you will understand it too. This is my transition from stage 2 to stage 3. From ultra-low interfacial tensions to super low dynamic surface tensions. From enhanced oil recovery, production of oil, to premature baby recovery from disease. So what did I do here, there? We, as I said, were studying lung surfactants, unprecedented super low dynamic tension, so there are a lot of problems to solve there. I started from the basic problems, I went to more practical problems. First, there were mass transfer effects, dynamic effects. I like those because that's a chemical, only chemical engineers presumably can do that. We studied adsorption, tension, equilibria, adsorption, tension, dynamics, one component, two components, non-ionic, ionic, etc. And then the most important result was we studied this surfactant, DPPC, dipalmitoyl phosphatidylcholine. This surfactant is the major ingredient of the lung surfactant lipids. Without this surfactant, we will not be breathing very well. So it is the major component, the major component. But there are other components. It forms liquid crystals above 41 degrees. Therefore, it should not really form vesicles. But we persisted, and we found basically, okay, the following. So we studied thermodynamics, dynamics, microstructures in solution, dispersion interfaces, and then the main contributions were the following. I will summarize 25 years of work in a few slides. We need, instead of going as some chemists or biochemists or biophysicists would go, try to study the molecular structure. Our theme was, molecular structure, of course, is important, but what is important is the function. What do these molecules do? Okay? These molecules, we discovered after a lot of research, in order to have very low dynamic surface tension, you have to have a surfactant that has the following properties. It has to adsorb fast and dissolve slowly. So, as you pulsate the area as you breathe, okay, surfactant adsorbs in the adsorption stage, okay, in the expansion of the area stage, and then it does not have time to come out. Therefore, you have higher surface density under dynamic conditions than under equilibrium conditions. And this is the reason, one reason, to have very low dynamic surface tensions. And then we actually experimented and we found out the main component, DPPC, has this ability. And this is a very typical result. I published hundreds of these figures. You see here, some surfactant has rather high surface tension, but once you pulsate the area, the surface tension goes below 20, super low, as we call it. So we found out, therefore, that there are simple systems that eventually could be used as a potential lung surfactant replacements. And we found 3 of them that have these properties, okay? I cannot claim we developed a new lung surfactant that can be used in real clinical cases, but at least we understood this system and we understood the effects of proteins, et cetera, et cetera. So we also went back to vesicles. Here, the vesicles performed much better than the larger particles. So in this case, we went from bad vesicles for interfacial tension to good vesicles. Okay? We also studied micellar systems, etc. Micelles were not so interesting. We were not able to find micellar systems that have this type of behavior. And we discovered, as I said, soluble surfactants. The traditional state of the art was soluble surfactants cannot do it. That's not true. They can, under certain conditions. And then we found out all these vesicles. These are microphotographs that were done in Israel by my friend, Professor Talmon. And you see how vesicles look like. We also see the state-of-the-art cryo-TEM controlled vitrification. So basically, you have a vesicular dispersion. You freeze it so fast that the vesicles remain intact, there are no artifacts, and even the water remains, not remains, but becomes glassy, so you can see things around. Right? So this, as I said, was a major project over 25 years. It involved 14 PhD students. You can see their names here. The most recent was Yunji Park, who is now at the University of Cincinnati, just started last fall. And then I collaborated there with many people. Dr. Hahnemann, Professor Linda Wang, she introduced me to adsorption. She is an expert on adsorption for chromatographic applications, both equilibrium and dynamic. So I learned a lot from that. She challenged me to explain thermodynamics of adsorption of mixtures. And then these two are ladies from Barcelona, Spain. They synthesized surfactants that we studied. Talmon is electron microscopist and chemical engineer. Professor Nassim, we studied proteins. Lauterbach, we studied infrared spectroscopy. Bassaran, who is not here today. Oops, now I can do it. Here? So, and then postpone, okay. So I'm happy that I provided additional entertainment today. Okay. So this is the third area. And then, of course, Professor Matalon, he helped us with some studies of lung surfactant applications. And then we started talking to my good friend, Dave Corti, a top fluid mechanics, molecular theory, and mass transfer and other talents. So I said, okay. We started studying the stability of the vesicles. In order for these systems to produce the right surface tension behavior, the vesicles had to be stable, okay? So the stability of the vesicles, and then we started studying the so-called LVO theory for vesicles. We used the so-called stealth liposomes, etc. And then this was approximately 2008. And then in 2008, Dave and I started a project motivated solely by practical considerations. Hewlett Packard had a program They were interested in the dispersion stability of pigment nanoparticles for the blue or cyan inks and other inks you use in your printer. And then also white inks, such as inorganic particles of titanium dioxide. This is the last stage of my career here. They were interested, how do you stabilize them? Just imagine if you have an ink dispersion. By the way, the inks that you have are not organic solutions, organic ink molecule solutions, but they are particles. They are nanoparticles. The pigment, the blue pigments are copper phthalocyanide, as I said. Just imagine if you have an ink cartridge of blue ink and then settles halfway. The ink on the top, it will be bad ink. And then if it forms a coagulate and then a solid material, you have to throw away the cartridge, you have to throw away the printer. So the inks have to be stable for a long time. Okay? So we started studying this with Dr. Dong, and then we hired also Aniruddha and Betty Young, who is right here, who is primarily responsible for this talk. So after we started studying colloidal dispersion stability, preventing agglomeration of small ink nanoparticles, in 2011, these people told us, forget about the blue ink. We are more interested in titanium dioxide white ink particles. Why? Because it's a very nice PhD chemist, very innovative, from Hewlett Packard, Houghty Inc. He called us and he says, you know, these particles are about 300 nanometers, and they settle even without agglomeration. Dave and I looked at each other and said, are you kidding me? These guys are totally ignoramuses. Turns out we were the ignoramuses, but anyway. 300 nanometer particles are colloidal particles. I have been teaching these poor students for 30 years that these particles have significant Brownian motion. I will tell you more about that. They would never settle on their own. These guys must be wrong. Probably the particles agglomerate, and then they settle. They didn't figure that out. I said, no. OK. Give us the money, and we'll do it. But you say, can you stabilize them? Of course we can. Or at least we will try. Dave and I, to be honest with you, don't quote me on that. Please don't record that part. We thought it would never work. But we'll have a nice project. We'll explain to them why it would not work. OK? Let's suggest other ideas to rescue them. And they said, this is a big problem, the white inks. They sell fast. And what do you do about them? Well, we have a big printer over there, and we have an operator. Every few days, once a week or whatever, he opens the printer, takes the cartridge, and shakes it. This is high tech. But they said, don't worry, we're considering other options. Recirculation, things like that. So at the same time, actually, Chevron, with Hari Subramania, an ex-Purdue graduate of University of Osman, he found out we were doing research on dispersion stability, and they also gave us a grant to study dispersion stability of hydrates for producing another dirty fuel, natural gas, and oil, etc. Okay? So let me introduce you, therefore, to stability of colloidal dispersions. A colloidal dispersion is a dispersion of particles that remain suspended for a while, and then, presumably, they aggregate, okay? And they settle, or they sediment. The degree of stability, as I said, affects the quality of the printing images. Okay? It affects the performance and maintenance of the print heads. And basically, it has to be avoided. The sedimentation has to be avoided. The pigment sizes range from 100 to 500 nanometers. There is a challenge of preparing stable dispersions, as I said. These particles have very high density, 4 grams per cubic centimeter, okay? And we did the experiment. Under some circumstances, they settle by about 1 centimeter over 15 hours, and that's bad. Much better than that. We have to have very good stability for good shelf life and subsequent applications. In the applications of inks, by the way, the main problem is to avoid sedimentation. If there is some aggregation, we don't care, because the ink nanoparticles will be deposited on a surface, and then they will stick there anyway. Who cares? OK. So the goals are determine now the key factors. Let's do some science here, sedimentation behavior, understand the stabilization mechanism of dispersions against both agglomeration and sedimentation. By the way, agglomeration is the term we use to describe sticking of particles. It can be either strong forces sticking, coagulation, or flocculation. Okay? So let's do some calculations. Colloidal particles traditionally are 1 to 1,000 nanometers, and nanoparticles, many people say nanoparticles is a brand new area, very exciting and all that. We, so-called colloid scientists, consider nanoparticles a wholly owned subsidiary. Okay? So what is the velocity or the speed of the Brownian motion? Okay? Let me tell you something. Some people know about that, and so I apologize if I bore you. But most people don't. In fact, I keep asking these questions to any undergraduate students who comes to my office. Do you know what is the velocity of a nitrogen molecule here? You say, I don't know. It's 500 meters a second. Can you believe that? Who didn't know that? No answer. A water droplet has 16 centimeters per second, and even a nanoparticle that we are interested here has a significant Brownian velocity. Okay? A lot of agitation. The sedimentation time is 0.2 micrometers per second. This may give you the wrong impression that this particle will remain suspended forever. Until then Rampke comes through. Okay? We start writing equations. Thank you, Dave. Okay? This is the convection diffusion equation for sedimentation and diffusion of particles. Okay? I would never dare to give a talk here without showing an equation of this kind. Okay? I hope that passes master, Rampke. Okay? So basically, consider dispersion. The particles have a velocity, sedimentation velocity, and have a diffusion coefficient. Okay? This is the equation. And the boundary conditions are 0 flux at x equals 0, 0 flux at x equals L, and then initial condition. Here I only consider the dilute limit, the monodispersed spherical particles, and no interparticle interaction or agglomeration. The main goal of this is to find out whether these particles will or will not settle. Okay? All right. So first we solve the problem, the steady state problem, and we found out that the concentration, this should be psi here, it doesn't matter. The concentration depends on the Peclet number. The Peclet number is the ratio of the sedimentation velocity to the diffusion velocity. And if the Peclet number, which is this, r cubed, delta rho g, etc., if the Peclet number is much larger than 1, they will sediment, whether you like it or not. Whether you like the definition of colloidal particles or not. So anyway, Peclet number, very small, much less than 1, the particle would never sediment. It's not a matter of time. They would never sediment. That's a steady state. Peclet number 1 is more or less the limit. So we called back Hao T. Ing at Hewlett Packard and said, look, forget about everything we told you before about colloidal particles. Just use the Peclet number. Okay? We wanted to convert it to chemical engineer. If the Peclet number is less than 3, even 3 is OK. At least this is a steady state. However, if the Peclet number is 10, 20, eventually all the particles settle. If you want to prevent sedimentation, the most important thing is to prevent the particle from settling completely, even at infinite time. Okay? You also notice here that we also have the viscosity here somewhere, well, or diffusion coefficient. Yeah, the viscosity here, this is the Stokes-Einstein equation. The viscosity also plays a role in the transient. Okay? So anyway, we played along with that. We also studied the time dependence. Okay? So now, for non-interacting particles which do not agglomerate, we know what's going on. Okay? Let's apply all this theory, which is not really very complicated unless you go to combine agglomeration and sedimentation. There are many problems there to be solved. For delta rho 3.2, the length also is an issue here. Okay? 1 centimeter, this temperature and this size. The Peclet number is 1,000. That's why these particles sediment no matter what. How T was right. You don't need to agglomerate to have sedimentation. And so then the obvious answer was to have truly colloidal particles for this example, the limit is 30 nanometers, not 100 or 1,000. Okay? And for every set of conditions, you can find out the limit of the Peclet number, the limit of size. Okay, so now we understand the problem. Even if we use the best surfactant to stabilize the dispersion against agglomeration, they will settle. And so we started being a little bit smart. Okay? Not too smart, just a little bit smart. Okay, let's solve the problem. Decrease the Peclet number. Right? Makes sense? Yes. I hope it does. Decrease the size. At that time, they sent us also some very small particles, 20 nanometers. We said, oh, this particle will never settle if we disperse them. We had a very hard time dispersing them. Very hard to separate. And so we gave up on that. And even if you spend a lot of money and effort to produce stable dispersions of 20 nanometer particles, which would never settle, okay? They told us the bad news. The inks that consist of 20 nanometer particles are bad inks. They don't have the right scattering properties, okay? So there is, in order for the ink to perform well, it has to have high refractive index and size in this range. So it's not an option. You may as well give up or just use the shaking method again. Okay, let's decrease delta rho. There are patents in the literature, attempts. Okay, let's have titanium dioxide particles and make them hollow. Very smart idea. Decrease delta rho, decrease Peclet number, problem solved. However, a bad ink. Impractical, because it has to have the right refractive index, scattering properties, etc. And this is meant as a joke. Okay? You have to go to the space shuttle to print something. Okay? That's even more impractical. All right, strategy number 2. Maintain high Peclet number, increase the viscosity. Well, let's increase the viscosity from 1 centipoise to 10 to the 3 to 10 to the 6. If something sediments in 20 hours, 20,000 hours would be okay. We'll get more money out of this. 20 million hours, that's good. And because of this equation. So we said, okay, let's start using surfactant dispersants. That's what we know what to do. Let's do it. And so we studied, these are some details here. Okay, the most important thing is this diagram. Which surfactant shall we study? I don't know. Let's try one. SDS. Let's look at my lab. Do we have any SDS left? Oh, yeah. We found some SDS. SDS is the most famous surfactant, single-chain surfactant. A lot of information is known about that. Conductivity, critical Micelles concentration, size, lots of things, hundreds of papers. Let's study SDS, for God's sake. Okay, now I will tell you the most exciting part we found. If we have no surfactant, sediments in 2 hours. Bad. Let's put some surfactant. Oops, 25 hours. Yes. What do we do next? Put more surfactant. Okay, put more surfactant. And then we reach the so-called critical Micelles concentration of the surfactant. Okay? 40 hours, we reach the brick wall. Then you start here. This is, we call it region 1, R1, R2, R3. You put more surfactant, instead of absorbing on the surface, it forms Micelles. So what's the conclusion? Micelles are bad. Okay? Or useless. Useless. Okay, and then we learned something that really surprised our sponsors and ourselves. You have, let's say, 1 weight percent surfactant is 40 hours. You put 2 weight percent surfactant, okay? It starts settling again. What's going on here? Micelles, not only they are useless, they are detrimental. How do you explain that? So we told the students to repeat the experiments. They said, there must be something wrong with you. By the way, we measure here the sedimentation times. This is how it looks like. This is a dispersion, type equals 0, at about what we call half time of sedimentation. Half of the top half is more or less clear. So this is the time that I have here. So 40 hours is the best we can do with SDS. And if we put more SDS, it's a disaster. Real disaster. So they learned something. Don't put too much surfactant, okay? Don't be too anxious. Okay? So there are 3 regions, detrimental. And then, of course, Dave and I always like to explain things. Let's explain this. What happens? Well, you know, the micelles are charged. More micelles, more charged particles. Everybody knows that if you put a lot of salt in an aqueous solution of particles, eventually you will have them aggregate. And if they aggregate, the size, the effective size from 300 nanometers will become larger, and therefore they will settle. Case closed. But Dave said, are you sure? Of course I'm sure. Can you test your hypothesis or speculation? I misquote you a little bit, sorry. I said, yeah, I can test it. Let's use 100 millimolar salt. Okay? If you have an electrostatic destabilization, what's going to happen? You're going to have faster agglomeration and faster sedimentation. Right? Wrong. Well, this is with 100 millimolar salt. Very similar behavior. Region 1, region 2. Here, close the CMC. Micelles useless. And micelles detrimental. It's not electrostatic. What is it? And then we remembered something we knew from teaching the courses sometimes. There are other forces among particles. They are called depletion forces. What's that? Let me try to explain. In fact, we may have a diagram later. If you have 2 particles in dispersion, okay, they aggregate a certain rate. Now, if you have some smaller particles, okay, and the smaller particles are excluded from the space between the 2 big particles, okay, the particles on the outside will have a higher osmotic pressure than between. And so the osmotic pressure difference pulls the particles together and causes flocculation. It's something nice. By the way, this is actually a very painful thing for Dave and I when we submit our paper. Some of the reviewers one of the reviewers said, depletion forces, well, everybody knows about depletion forces. There's nothing new here. Well, nobody, however, has found out that the depletion forces at this concentration can cause such a bad effect. And depletion forces, you don't know quantitatively whether they are negligible or significant. So we disagreed with the reviewer, and we managed to convince the editor to publish it. So this is about to be published now. Okay? And then actually we even explain why at high ionic strength, okay, the concentration at which the transition occurs is higher, okay, because it has to do with the suppression of the double layer. These are some minor details or technical details, not minor, that I'm not going to cover in detail. And then we started studying the classical colloid chemists or chemical engineers. We studied how much surfactant absorbs as a function of concentration, okay? As you put more surfactant below the CMC, more surfactant absorbs, and the sedimentation rate increases, sedimentation time increases, which means you prevent sedimentation, okay? Then we also studied the surface potential, zeta potential is called, okay? And the particles become negatively charged, okay? And in water, the particles are positively charged, but eventually become negatively charged because the SDS is negatively charged here. And so it's a very classical example of electrostatic stabilization. Okay? And then we started applying the LVO theory. Okay? I know some of you came to listen about the LVO theory, so I have to explain some things. So basically here, the LVO theory says the potential energy of interaction divided by KT, the dimensionless potential energy of interaction, involves attractive interactions, repulsive interactions. The attractive interactions are described by the so-called Hamaker constant and the size and distance terms, and also electrostatic repulsion stabilization, which I describe. I'm sorry, this is the attractive and this is the repulsive. And then the whole potential of interaction has a big potential energy barrier, which is about 120 kT. 120 kT means that these particles will never aggregate. And there is a so-called stability ratio, which I will explain very briefly. Stability ratio is the ratio of the rate when all collisions lead to sticking, divided by the actual rate. The inverse of W, if let's say is 10 to the minus 6, means one collision in a million produces an agglomerate. Ideally, we like to have stability ratio of 10 to the 9, 10 to the 12, okay? And then we calculate, based on classical theory, the stability ratios here were enormous. So let's put the positive things first. Region 2, the stability ratio is so high, the particles will never coagulate. They just settle like a rock. So this explains region 2. Region 1, not quite. Not quite. It should be completely stable, but it is not. This, we believe, has to do with some assumptions in the LVO theory, okay, that are not correct. For example, that the surface charge is completely smeared on the surface, whereas the surface charges are discrete. And there are other problems. The zeta potential is we assume is the same as the surface, the zeta potential is the same as the surface potential. That's not true. So basically, this theory needs a lot of work. So it's opportunity for future research. This is a classic problem that has a solution which is not satisfactory. We have many other problems we found with the LVO theory. Okay? And so, however, in region 3, the LVO theory provides no explanation. The LVO theory says these particles will not coagulate, but they settle. Therefore, they flocculate. Flocculate because of dispersion forces. Okay. And then we put the depletion, not dispersion, depletion forces. We put the depletion potential interactions here, and we saw how this barrier changed, and two things happened. The barrier became smaller, but still it was large enough to prevent coagulation. And then we started having a deeper secondary minimum, as it is called, which is the reason for weak flocculation. Okay? And we explain some other things here. Instead of going to this, I have several more minutes. I want to discuss now perhaps the most exciting part of this talk. I leave it for the end, okay? Strong end. Let's face it, okay? The best we can do with this STS is 40 hours, okay? We could have been more honest to ourselves and to Hewlett Packard and say, you know something? We failed. But we told them, you know, you can use them for other systems, all this knowledge. Nah, they say it's not going to fly. If you want to have the second and third year grant, you got to produce something that we can use in our commercial division. Uh-oh. So we decided to start screening some surfactants. I had lots of surfactants left in the lab from the last 25 years. And so Betty started screening some surfactants. Out of 12 she screened, she found one. This one looks a little better than the others. Oh, which one is it? Okay, DDAB, remember? DDAB. We had some of that. DDAB is a cationic double-chain surfactant. Therefore, it does not form micelles, it forms vesicles or liquid crystals, or both. It has very low solubility in water, that's important. Unilamellar vesicles, and then we prepare them very simply, not very sophisticated. Forget about sophistication. Just stir them with a magnetic stirring bar. We call them stirring process, or you can sonicate. Those of you who are familiar with liposomes know that we sonicate them, okay, to produce smaller vesicles. And now here is a real interesting result. Half weight %, okay? In 1 week, it has settled. Both the stirred, this reminds you of James Bond movies, stirred or stirred and sonicated, okay? Shaken and stirred and sonicated, okay? So half weight percent is not good. Remember, SDS, you put more surfactant, it becomes worse because of the bad micelles. How about the good vesicles? 1 weight percent, better. And look at that. 2 weight percent, a month and a half, 4 months. We solve the problem, really, with 2 weight percent surfactant. And of course, you can play around with the parameters, the procedure, the method of preparation, the concentration, etc. Perhaps salt, we didn't try all that. This is a wide open area. This is the first ever stabilization against sedimentation. Okay? All right? So this is a major discovery. We applied for international patent application. This is the first time, actually, we're disclosing here the molecule, okay? So we will use the Italian code of omertà here. Don't talk about it. Okay, what is going on here? What's the idea? If you have vesicles, okay, if you have 2 weight percent surfactant, let's say half weight percent surfactant, for my cells, the volume fraction is half volume percent, roughly. But if now you open up and you form little balloons or vesicles, the half weight percent is about 20 volume percent. It's a concentrated dispersion. The 2 weight percent, we estimated it, is probably about 70%. We have a close packed dispersion of vesicles at a low surfactant concentration. Okay? And that's why the more surfactant, the better. Okay? Now, of course, this was in our imagination. Okay? Let's see the proof. We did some controlled vitrification, cryo-TEM, and we believe that these results are quite reliable, no artifacts. And so half weight percent, you see, is quite concentrated. 2 weight percent stirred, not, let's see if you can see it well. Oh, yes. What do we see here? You see the vesicles are so concentrated, okay? The volume fraction must be beyond the volume fraction of close packed spheres. In fact, this reminds you of a foam. That's what a foam is. A foam can have 90% air bubbles, okay? They are deformed, okay? So just imagine now that you put here a little particle of titanium dioxide. Okay, first of all, the vesicles themselves don't move, okay? I was talking to Professor Wang here, and I said, the vesicles remind me of what happens to you when you are in the middle seat in an airplane and have 200-300 pounds people around you. You're like this, okay? All right? If you sonicate, however, sonication here makes it worse. So if you use, for example, 2 weight percent, you sonicate, you may have to use a little bit more surfactant to make sure you have, this is the optimum. This is the basic idea, okay? Now you put a little titanium dioxide particle over here, and you see it's like in the airplane, you know? It cannot move. All right? They prevent them from moving. They don't move at all, period. They can stay there for years, hopefully, although the lifetime of a graduate student is not that high. But we'll keep the samples, okay? I will report back in 5 years if anything's settled. They are trapped. However, someone says, well, I know I can use molasses, I can use a gel, the particle will never settle, right? But this would be a bad ink. Okay. How do we know they don't move? Okay, this is more technical for those who know about dynamic light scattering. Dynamic light scattering is used to measure the diffusion coefficient of particles in dispersion, from which the diffusion coefficient you measure the size. And you have correlations in the fluctuations of the intensity, and you have the so-called autocorrelation function. And if it goes like this, you fit this equation to this curve to an equation, you find out the diffusion coefficient and the size. And you find the size is right. Now, when you have a dispersion of vesicles at high concentration, close packed, you don't have individual particle diffusion. Okay? In fact, this is a very tough problem to solve. We don't really know how to interpret this, but it gives you more evidence that the particles, the vesicles, are really very close packed, and they don't move like individual particles. Okay? How about the viscosity now? If the viscosity was so high that the dispersion does not flow, then it's a useless result. Because for the inkjet printers, you must have low viscosity. If they don't flow, forget about it. Thankfully, the viscosity is not very high. It's about 10 centipoise. This does not explain the phenomenon in a continuum mechanics sense. Okay? And of course, I remembered my good friend Jim Carruthers, who said, oh, you can find a non-Newtonian fluid. The best is to be time-independent, shear rate-dependent viscosity. And thanks to Professor Won's laboratory, we were able to measure the viscosity now in a constant shear rate or constant shear stress to find out the viscosity as a function of shear stress. And look what we found. That's very nice. This as a function of shear rate translates to shear stress. Look what happens here. This dispersion has about 10 centipoise viscosity, the same we measure with a capillary viscometer, but at lower shear stresses, it has 10 to the 3 to 10 to the 6 or even more higher viscosity. And the important thing to note is that when a particle flows in a suspension based on the gravity force, the stress around the particle is very small. So the viscosity that the particle feels is the viscosity at low shear stresses, and the viscosity that the dispersion feels when it flows in gravity is this viscosity. So basically, the behavior in terms of rheology has to be like this. So we discovered the behavior in terms of rheology and the behavior in terms of structure. Okay? So many people, of course, ask how general that is. Okay? We are looking for new dispersions to stabilize for a fee. And Professor Alex Way, I was talking to him 2 months ago, and he said, we have some particles, magnetic nanoparticles. They settle within minutes or hours or whatever. I said, oh, I can stabilize them, no problem. So he gave us a sample, and actually we gave him a sample of our vesicles to try. And of course, good to his terms, he sonicated them, so he destroyed the structure. And he said, it doesn't work. Uh-oh. But then, of course, we got the particles, we did it in our own way. And those dispersions, as far as we know, Betty, they are still stable. They haven't moved a bit. So it's very general, actually. So it's a very general method. Unfortunately, it cannot apply to systems for which you cannot keep the surfactant inside. Anyway, all right. So I'm close to the end. What are the conclusions of this research? Surfactants can be very useful as dispersants. You must use the Peclen number, okay, to define a colloidal, non-sedimentic particle. And, the closed pack, so basically the basic idea is closed pack vesicles can produce a good optimal combination, good stability against sedimentation. They affect the rheology of the dispersion, and the key is to produce high viscosity at low shear stresses, low viscosity. This idea actually is not entirely new, okay? People in the cosmetics field, they have used it using polymers. So we don't make a claim that the idea is completely new. And in this case, Micelles do not help, and they can be detrimental. In addition to these conclusions, it's traditional for this kind of seminar to have a few words of wisdom. I don't know if I can do that, so I just call them other conclusions. Choose good students. That helps a lot, because they do all the work. Choose good collaborators. Okay? I gave you some examples of those. Use a variety of, it should be experimental tools to the same goal, and use experiment and theory. And the other thing is, follow your instincts. In university, we can afford to do some fundamental research without having the immediate application imminent. Okay? May come later. And then do not throw away your old surfactants or other materials. You never know when you might need them. Okay? I'd like to thank you very much for the opportunity to give this seminar, and I will be happy to answer any questions. Please, go ahead.
Questions?
Yes, sir.
Thank you for your talk, Professor. I've got two questions. The first one is regarding EOR. So, the way use of polymer is used in the injection well as well as the surfactant.
Yes.
I was wondering if you could comment, based on your student experience, on what exact role of the polymer is on enhancing oil recovery, whether it's actually due to achieving property or depletion force, or is it a combination of both, or is it a split
Okay. Thank you. I understand the question. This gentleman asked about EOR, enhanced oil recovery, in which the percent recovery of oil can be improved not only by using a system with lower interfacial tension, but also using polymers. It's called polymer flooding. The polymer flooding role is to increase recovery by decreasing the so-called interfacial instability. Okay? When a low viscosity fluid pushes a high viscosity fluid in a porous medium, okay, the interface is unstable, and so eventually it forms, so it's not flat, you don't have a flat front, and therefore the stream of oil is not continuous, and therefore it breaks up, and then the recovery is poor. Using a polymer solution, some kind of polyelectrolyte, increase the viscosity of the water, of pushing fluid, and therefore it decreases the interfacial instability. So it's not related to the interfacial tension. So this is one measure. It is cheap, but it has a limited ability to dislodge the oil droplets, okay? Because the interfacial tension problem remains. So in the past, and actually this area now came back to fashion the last 5-10 years, although now with the price of oil dropping again, it's like reliving the 80s. Lots of people from oil companies and oil service companies are being laid off, just as they did in the mid-80s. Many of my good friends who went to work for industry were laid off and then they went to academia. And so polymer flooding is there. So that's the first question. Polymer flooding is to increase the viscosity to decrease the interfacial instability. What's your second question?
The second question I had is just regarding EVAP. So you very nicely showed that the physical structure that forms is conducive to the lower tension that we're looking for.
You're talking about DDAB? You're talking about DDAB?
Yes,
DDAB, we do not consider any tension there.
Okay.
No surface tension, only the structure of the dispersion.
Okay.
Yeah, continue.
I was curious as to how the role of the actual, what your actual rules of thumb you use in terms of selection of the chemistry for...
Selection of the chemistry. It has to produce high volume fraction of aggregates, of particles, of surfactant particles or aggregates, for low volume fraction of the actual surfactant. That's one. If it is double chain surfactant, it's more likely to form vesicles than micelles. So most single chain surfactants, I expect them they will not work unless you use 50% of 50% of surfactant, which sometimes doesn't even dissolve. Okay. It can be ionic or non-ionic. It doesn't have to be. Okay. So there are many opportunities here to find other surfactants that work. We believe we can find other surfactants. Okay. This is not the only one. This was a lucky incident, but we can find many other surfactants, I think. Okay, thank you. Other questions? Yes?
So you said the LVO theory did not agree with your region 3.
Yes.
So did you include the depletion forces in the model and see whether it agreed better?
Yes, yes. Basically, if you have a potential energy curve of interaction, the total potential energy curve, the barrier, the coagulation barrier, okay, remains high. So therefore, we know there's no coagulation, and we tested that experimentally, we proved it, okay? For example, if particles coagulate, they cannot be redispersed without mechanical energy, whereas these particles that flocculated were redispersed just by stirring and by dilution of the surfactant. And when we introduced if you introduce the depletion forces, then you have a secondary minimum, which basically means that almost all the particles that come close together, they have a chance to flocculate. But actually, it's interesting, the flocculation, because it's not a very deep well, the flocculation can be reversed a little bit. The energy is not very high. Okay, so when we put, in a sense, we assume that the stability ratio for flocculation is 1. And in fact, we also have an interesting model that Dave and Niruda Kelkar developed. We predicted the total sedimentation time in region 3 by saying individual particles aggregate very fast, then become bigger. As they become bigger, they diffuse more slowly, but they settle faster. So in a sense, we found out what would be the sedimentation time of fast aggregating particles. This is actually another interesting problem we started attacking. So therefore, to answer your question, we put both of them, and we found out that they flocculate, and then if they flocculate, they don't need to agglomerate, or to coagulate, I should say. Yes, sir. Others?
I have to put in a question on the LVO.
Yes, yes.
So, you know, in observing all the discrepancies that you see, and from judging from your words, the main source of problems has to do potentially with if you continue on the phase model and lack of heterogeneities that are involved. Is that
This is one of them. Basically, we had some interesting experimental results in the previous project with copper phthalocyanine particles, where we found out that as you increase the ionic strength, when you expect that the surface charge density to decrease by more adsorption of the counter ions, we found the opposite, which showed that the co-ions adsorbed. Because imagine, the theory assumes that basically you have ions close packed on the surface. But in reality, you have an ion here and an ion there. So the surface also is available for adsorption of both positive ions, and therefore the continuous or uniform surface charge density is a major problem. Second major problem has to do with the fact we don't really know the true surface potential. We assume it is the same as zeta potential. That's second. Third, there are, actually somewhere in the literature, there are problems of non-smooth surfaces, heterogeneities, and then there are also problems with knowing the precise value of the Hammaker constant. So all these 4 problems, sometimes they work, makes you very happy, you teach it in the class, but then you realize there are other problems, okay? In the previous, in one paper we published 4 years ago with Dr. Dong and Dave, we found out that the stability ratio at high ionic strength should be 1, and it was 10 to the 5, the measured one was 10 to the 5, 10 to the 6. So we only had about 6 orders of magnitude error, which for kinetics, that's not bad. Just kidding. Yes, yes, sir.
After the depletion, do you know if anyone has incorporated the depletion forces into an aggregation frequency?
I'm not, I don't know the answer to that, but I wouldn't be surprised. Okay. Yes. Arvind.
This was a great seminar, but I thought you may say a few words about Dr. McNaby's book.
Oh.
Now, early on at the
Yes, I put it over there, yes. I would be happy to. I thought it would be another talk, but I would be happy.
Professor Franses has got this course for the sophomores for generations.
Yes.
And he has verified the sophomores by doing that. He has written the book. And I was asking
Yes, I would be happy.
the other day, how do they like the book? They're still terrified, actually.
They're still terrible. Actually, Thermodynamics is an interesting topic, and it is known to be abstract, and that's one of the reasons. So the way I wrote the book was to introduce the concepts of thermodynamics in a more practical vein. And the practical vein would be, if you know that an easy way to measure the enthalpy, to measure the entropy, then it's less abstract. It's very easy. Okay? And in fact, I have been interviewing everybody who comes to my office, trying to embarrass them. How do you measure entropy, Professor Varma? Not you, of course. It's an example. And they said, how do you measure entropy? What do you mean? It's in the steam tables. It's in the literature. I said, where did it come from? And so I wanted to educate, even from the sophomores, that measuring the entropy or the enthalpy is very easy. And let me tell you how you measure it, as an example of what is in the book. If you say the entropy of water at 25 degrees, liquid water, and 1 atmosphere is whatever, 5 joules per Kelvin per mole. Where did this come from? What did you really, do you have an entropy meter? No. I looked into Google, entropy meter, no answer. What do you have to measure to find the entropy? Let me tell you what you have to measure. Very easy. You have to buy a calorimeter, $50,000, and measure the heat capacity of liquid water as a function of temperature and pressure, and have a model. Not just the value there, but have a model so you can find derivatives. Is that easy? Yeah. Then you have to measure the equation of state, the volume as a function of temperature and pressure. Is that easy? Yeah. Then you can calculate the entropy and the enthalpy and the internal energy. That's how they're found. So if you know that, at least I think, which is not available in other books, that's the reason I wrote the book, then you know that this is not so abstract. You can measure it. It's something you can measure very easily, indirectly, of course. And then you can use it. What do you use it for? What do you use entropy for? What is the use of entropy? The entropy use is, it can tell you whether a process that satisfies the mass and energy balance equations and the momentum balance can occur or not, in this direction or in the other direction. If you know that, then you know, I call it the constitution of the physical world. So you should know that. And instead of knowing, like you know in the high schools or in the freshman year in chemistry, entropy is disorder. And someone says, what is disorder? How do you define it? How do you quantify it? How do you measure it? Is it of any use? Not at all. Throw it away. I have in chapter 14, however, an explanation. If you want to understand what entropy is from the molecular point of view, I have an explanation. You have to know all the thermodynamics 100%. You have to know the principles of quantum statistical mechanics. You have to know discrete energy levels of systems, not of molecules, and the two major principles of statistical mechanics, and then you can start understanding the molecular origin of entropy. I thought that was too hard for sophomores. And then also I wanted to teach sophomores that even though the entropy is useful, the most important quantities in thermodynamics for chemical engineers are the Gibbs free energy and the chemical potential or fugacity. And so the reason for that is to motivate them is I use the following suggestion. Okay. If you want to know whether mass will be transferred from this location to this location, it's very easy to do, or at least in principle. You have to calculate the mass of the system and surroundings before and after. You have to make sure they don't change. Okay? The mass is conserved. The energy before and after. I have to go in a few minutes, yes. And then you also have to calculate the entropy. You know how difficult it is to calculate the entropy of a solution of water, ethanol, or whatever. You will never understand this unless you know the Gibbs free energy. The Gibbs free energy says You only have to calculate before and after the Gibbs energy of the system. Forget the surroundings. And then, of course, you have the chemical. So basically, I introduce things like that to make it easier to understand and easier to see the application. Okay? The students at the beginning of the course, this semester, last semester, said, we'd like to see the practical implications, but you have to learn the principles first, and then we have the applications to phase and chemical equilibrium. So this is sort of a preview. And we have to finish. Thank you.